Elastic potential energy is energy that is stored in an object as a result of being able to give it a reversible deformation. Elastic objects, things that are able to be deformed and then will pop back to their original shape, are able to store elastic potential energy. Things like a spring, a rubber band, a bungee cord, a trampoline, and so on. The elastic potential energy is stored until the force that deformed the object is removed and the object springs back to its original shape. Be careful, objects that can be deformed but that do not bounce back to their original shape are not storing elastic potential energy. So, for example, I can crush a cardboard box, but that box does not have elastic potential energy. We conducted an experiment where we applied a force and compressed a spring and then measured the energy that was stored in the spring. And we found that as we applied more force, we were able to compress the spring further, and the area under that force versus displacement graph, it equaled the work that we did on the spring, and it also equaled the elastic potential energy that was stored in the spring. So as more force was applied so that the end of the spring was displaced further, there was more energy being stored in the spring. And that's represented here by the pie of energy getting larger as the spring is stretched further. That work that was done as we applied a force to the spring and compressed it is equal to the elastic energy that was stored. And we derived an equation that said that the elastic energy equals half of the spring constant K times the displacement of the spring squared. Remember that the spring constant K was the slope of the force versus displacement graph. So, when a spring is stretched or compressed, it's storing elastic potential energy via that restorable deformation. And the equations for calculating elastic energy, if you want a snapshot at a point in time of the elastic energy in an object, you multiply half of its spring constant times the square of the displacement of the end of the spring. If you'd like to know how much the elastic energy has changed as the displacement of the end of the spring changes, you take half of the spring constant times the final displacement squared minus the initial displacement squared. In order to get the elastic energy in joules, you must use standard units. And so the spring constant K needs to be in units of newtons per meter, and the displacement of the end of the spring, that's called delta X, that needs to be measured in meters. There are a couple of examples in the student packet on page 18. This is in section D. So let's look at number 6 and 7 here. Number 6 says that a bungee cord stretches 25 meters and it has a spring constant of 140 newtons per meter. And so if we'd like to know how much energy is stored in that bungee cord, we want to look at the elastic energy. It should be half of the spring constant times the displacement of the cord squared. They gave us all of this information in standard units, and so in this case we can just plug in. It's half of 140 newtons per meter times that 25 meters squared, and so we get in this case, 43,750 joules of elastic potential energy stored in that bungee cord. Another example is number 7 here, where we have a railroad car spring. And they don't give us a spring constant, but they do tell us that the spring requires 10,000 newtons of force to be applied to compress it 3 centimeters. Well, from Hooke's law, we know that the force applied to a spring to make it stretch has to equal the spring constant times the displacement of the spring. And so if I want to solve for K, that would be the force that had to be applied divided by the displacement of the spring. Now I do need to be careful and convert this 3 centimeters. That's not a standard unit. So I know that there are 100 centimeters in a meter. So 3 centimeters is 0.03 meters. Okay? But then, so the K would be the 10,000 newtons divided by 0.03 meters. And so we would get a spring constant of 333,333. So it's a railroad car spring. It's a very, very stiff spring. So it takes a lot of force to make this spring deform. Okay, but now that we have the K, it's asking us for the energy that's stored when it's compressed by 10 centimeters. Again, I need to make that 10 centimeters a standard unit, which would be 1/10 of a meter. So the elastic energy in the spring is half of the spring constant times the displacement squared, which would be half of 333,333 times 0.1 squared, which would be 1667 joules.